12 responses, which is good. So let's come back together to take a look at it. So what do you think of those two videos? Kind of silly, but relate a little bit to what we've been doing. So just take a look at how we're feeling. I like that Google Forms gives us an instant analysis. So let's see what you took from this. Very good. It looks like almost all of you got that. What Brian is saying to Peter is that he is so fat, he has so much mass, he's generating his own gravitational pull that will literally pull objects into orbit that are near him. And theoretically, the reason why Brian throws the apple at him rather than just holding it and letting go, did anyone figure this out? If he held it next to Peter and let go without throwing it, theoretically, what would the apple have done?
Fall to the ground.
I mean, it would have fallen, but it wouldn't have fallen to the ground. It would have fallen where? I mean, if he's saying that Peter has his own gravitational force, if he just held the apple, it would have just fallen right against him, right? Which is the equivalent of falling to the ground, right? He's saying that Peter now is his own ground, right? That he's attracting things, but he had to throw it with a tangential velocity, which looks like some of you are getting at. Hitting the escape speed, kind of, if it hit escape speed, it would go out of orbit, right? But you need that tangential velocity, the vertical sideways motion that is getting it to the point where it's falling around Peter. So obviously this is a flawed argument, though it looks like we had some mixed responses as to why. The correct reason is that everyone exerts a gravitational force, right? Each of you is pulling on everyone else in this class, even though we're in all different parts of the world right now. You are still exerting a gravitational force on each other technically, right? It's just so small and minuscule that we don't notice it, and we don't even consider it. You know, we tend to focus on the scale of planets and things like that. But in reality, what Brian is saying is true for everyone. They're just exaggerating the point. There's a lot of reasons why this is silly, but if you do the math, the correct answer I was getting at here was indeed what about half of you got. It's that in that equation, the value for g, the gravitational constant, is a super small number, right? It's times 10 to the negative 11, which just shows that gravity is actually an incredibly weak force. And so the mass numbers need to be absolutely huge to actually get a significant amount of gravitational force in newtons. And so there's no way that Peter, as an overweight man, could achieve that unless he was like extremely dense, which again is not going to happen on Earth. The next video I thought was kind of interesting. I had no idea Rube Goldberg is indeed, he was a cartoonist, worked in like the 1910s, 1920s, drew political cartoons, and he drew cartoons of these goofy machines. And it looks like most of you, about 3/4 of you, didn't know that, and I didn't know that either. So I thought he was like a retired physicist or something like that that was just playing around. All right, any other questions on that? Our goal today is to continue to explore the idea of orbit and how gravity influences that. So again, we're just continuing on projectile motion, but moving into the later part of chapter 5 that we went over earlier. The next thing that I'd like you to do, I hate to sort of repeat the task, but again, I'm gonna have you watch 2 videos and answer some questions on them. These are a little more serious and a little bit longer. And since I've been using Edpuzzle and everything repeatedly, I want to change things up. So what I made was a discussion board. So you want to click on that link right there under task 2, U4L17 satellites in orbit and gravity visualized discussion. This is what the Canvas discussion will look like. And I have the 2 videos listed, and the first video is all about how do we get satellites into space and get them to stay in space. There are 3 questions you need to answer related to that. The second video is a sort of in-class demonstration of Einstein's idea of gravity, and there's 2 questions related to that. And you can answer these in bullet point form, you can number them, you can write 1 long paragraph, doesn't matter to me. You'll see there's responses from my previous class already, but that's okay, or you might not be able to see those, I don't know. But just hit reply and type your answers. I'm gonna give us about 10 minutes to work on this. And as usual, I'm here listening if you have questions, if you're not sure what to do. So go for it, and we'll check in 20 minutes, because each video is probably about 5 minutes long. So, oh, and I should emphasize too, before I forget, The second video right here, Gravity Visualized, is 10 minutes long. I don't want you to watch the whole thing. Just watch the first 5 minutes. That's all you need to watch is the first 5 minutes of that video, and then you should be able to answer those 2 questions. So again, I'm going to set the timer for 20 minutes. I'll keep an eye on our submissions. Let me know if you have questions. Go for it. All right, kiddos, 20 minutes has passed. Looks like all but about 4 of you have managed to make your discussion posts. Let's come back into the room to review. What y'all think? Somewhat interesting? Not really? Looking at your answers on the discussion boards, looks like you were taking away the key things. So the 2 questions I just wanted to look at really quickly was, first of all, I thought it was nuts to learn about the idea of the fact that some satellites are deorbited and some are just launched away into what they call a disposal orbit, where it's basically like, all right, that's our trash heap of, satellites outside of Earth. So, I mean, what did you think? Are you guys okay with that idea of that we just launch them into a really wide orbit and don't worry about them anymore? Or, should we be deorbiting all these satellites? What were some of your thoughts? I guess the other question I should pose to you is, do you think that sending satellites into a disposal orbit around Earth, do you think that's a form of pollution? Cora, you're nodding your head. You think so?
Yes, but also because sometimes they come back down to Earth, or like they end up in the ocean. So it'd be kind of interesting if we created like this bubble and we just like shot trash up there and like got it out, and then somehow it like just disappears in black hole. That'd be
yes, yeah. If we could send it away from Earth, I think that the reason we're not doing that, right? Because that's a big question, especially for things like nuclear waste. Like why aren't we just firing nuclear waste out into space? And the point is that it's one, the risk of a rocket exploding with nuclear waste on it is pretty dangerous, but also that the amount of energy needed to get that trash and waste to escape velocity outside of our solar system is more expensive than it would be to just dump it somewhere else. So you make a good point about that there is sort of a cost limitation to it. And yes, I like your point that these satellites are still going to come down. It's just going to be years from now, and so it's kind of interesting that something that was satellites that were launched in the 70s might not be crashing back down to Earth till like 2050 or 2060. And then it's going to really impact people. The other thing, I don't know if anyone's seen the movie Gravity with Sandra Bullock. Does anyone know what other danger all of this refuse in space poses to humans? Yeah, right. It's stuff that can impact. The whole premise of that movie Gravity is that some of this projectile trash suddenly gets launched into a very fast orbit. And so these things all basically become bullets that are circling around the planet constantly. And so any astronauts that are in space, any space station is going to get totally torn up and destroyed. And the more of these satellites, I mean, yes, space is big, but the more stuff we send up there, the more likely it is that it's going to hit something else that's important up there. So kind of interesting problem. I think we should be deorbiting things as much as possible, but it's not how they've been thinking about it. So the other thing that I didn't realize, I mean, I guess it's kind of obvious, but it's weird to think about, is that every planet in our solar system rotates the same way. Did anyone realize that? Or at least, I don't know, that never struck me as unusual until I thought about it, that, if you think of Earth as going clockwise, every other planet is also rotating clockwise. And a lot of you got at this from his demonstration. What happened? What happened to everything else that was going in the, quote unquote, wrong direction or the other direction? Yeah, blew up, exploded, right? It's all gone. So, anyway, just kind of interesting to think about and how long it probably took for that to sort of establish itself. All right, so now I want to do an activity, which is based on the most recent video you watched. I know that you're not all going to have some giant hollow table and a huge piece of spandex that you can use, but I kind of played around with a couple things at home, and so I'm going to have you guys do a flip grid where you're going to try to simulate that. So the flip grid assignment is titled Gravity Visualized. I have a link for it right here on the tasks list. It is number 3 right here. And so just click there on the flip grid. I have a little instructional video. It's about 6 minutes long that I recommend you watch. But basically, you're going to need some kind of bowl or a pie pan or something like that. You'll need fabric, like either a running shirt or a t-shirt or a towel, or you can just use cellophane if you have plastic wrap, or even like a plastic trash bag works well. Clips or a tie or something like that to attach it to the bowl. Some kind of round object like a ball, could be a tennis ball, a cross ball. If you have anything else, you should check out any like board game stuff you have. They often have little balls in them. You'll need a fork or a knife, and you'll see how to do it in the video. But you just need to film a Flipgrid video of 3 things. One, showing that the satellite, when you have a mass in the middle, it falls towards the center, which is exactly what the guy did in the video. And then launch your satellite parallel to it sideways and try to get at least 1 full rotation. And give a brief description of what's going on, kind of related to what Einstein's doing. Again, my video will explain a lot of that. I'm going to give us the next 15 minutes to work on this, I think. I would like to come back with at least 5 minutes to talk about homework stuff. So we'll come back at 9:35. So let's plan for, let's see, it's 18 now. So let's plan for 17 minutes to work on this. And if you don't get done, it's okay. It'll roll into homework. So my other class was able to get mostly done. So 17 minutes and we'll reconvene to review. Let me know if you have questions or if you need help or advice or resources. Go for it. Let's come back into the room. All right, how was that? Looks like we got 11 responses, which is pretty good. So there's about 4 of you who still might need to do that. If you can't get Flipgrid to work, I know some of you haven't been able to upload videos. Again, you can always just email them to me, and that's fine. You guys were all bending the fabric of space-time. So for explanations, I was seeing a little bit of confusion. Some people were talking about center of gravity, that kind of thing. Again, it's just the idea that, you know, was Einstein's theory of relativity, that there's no real force of gravity. It's more that masses are bending the space around them. And so we can use that fabric as sort of just a very simple example, but you kind of have to imagine that in a 3-dimensional way, that there's sort of like some kind of curvature that a ball would follow downwards. So we're using Earth's gravity, you know, creating basically a little crevice that things roll down into or roll around. But it's a nice little demonstration, I think, or you know, it's sort of what Einstein was getting at about how he thought gravity was working. And it's cool in the video that you can see the guy even gets sort of, he has the sun in the middle, the really heavy weight. He sends 2 spheres around, like 1 for Earth and 1 for the moon. I don't know if you saw in the video, but you can kind of get the moon to also orbit the Earth as it's going. So we'll use the LaFette simulation to review that. I meant to go through and check your feedback, but I forgot to do so for the midterm comments. That's just the one thing you need to make sure you have done. So I'm going to go through and read those now, and I'll give you 10 points of an assessment score if you've got it completed. If not, I'll check in with you. So if you have not done so yet, please make sure you've read your comment and answered those 6 questions in the associated doc. Otherwise, your only homework for Friday is to complete anything you didn't get done here in class. So make sure you have answered the 5 questions on the discussion post on those 2 videos, and you've posted your Flipgrid video. Otherwise, I would like you to read Hewitt, chapter 28.1 and 28.2. So we're moving our way towards the last chapters of the textbook. And I'd like you to do now reading quiz or anything like that for Friday. I just want you to do the reading check questions. These questions are from page 815 or 849. It's right at the end of chapter 28. And I want you to do the odds 1 through 9. So 1, 3, 5, 7, and 9 should be straightforward. And we'll review those at the start of class when we meet again. Any questions on that? Any other comments or anything on the activity? Most of you did a pretty good job.
Question in a second.
Yeah, okay. Well, I'll hang around here in the room for any of that stuff if you want to check in about anything. Otherwise, thank you very much. Have a good day.
Thank you.
Mm.